All right, before we get into the specifics of binomial probability, I want to do a couple of reminders. This is something that came up back in week 7, and it's just a reminder of the idea that there are more than one type of probability. Most of our time and effort has been spent on the first of these, which is theoretical probability. What should happen? It's what we calculate. And those are the types of probabilities we've been finding for the most part. When we did our simulations, we were kind of looking at the other type of probability, which is experimental probability. Instead of just calculating it, it's the result of an actual experiment or an activity, or you could say a simulation for that. Experimental probability is also known as relative frequency or empirical probability. This is one you'd probably see more often than relative frequency. But basically, there are two different types of probability. I want to make sure just to remind you of that. Theoretical is calculated. Experimental is when we actually perform some sort of experiment. Finally, last reminder, this probably resonates pretty well, but the most important thing about probability is when we're looking to calculate a probability, what we're looking for are successes over outcomes. And so successes over outcomes is what we're going to look for when we're after a probability. That's not going to change today when we look at binomial probability. There's a discussion of this in your book on page 402, but it basically says the same things that I just did, but you might want to look that over just as sort of another way of hearing it. Any questions on this before we continue into some calculations? Okay. Let's say we were going to flip a coin 3 times. And you could phrase this question differently and say, flip 3 coins at the same time. It would be identical. So if I had a quarter and I flip it, I write down what it is, flip it, write down what it is, and flip it, write down what it is. It's not really any different than having a penny, a nickel, and a dime, flipping them all 3 at the same time and seeing where they land. So as far as those things are concerned, there's not really a difference as far as we're going to approach it anyway. If we were going to flip a coin 3 times and we want to figure out the probability of getting exactly 2 heads, one way we could go here, and I don't want you to write this down, one way we could go here is to make a tree diagram for this. Because I see exactly 2 heads out of 3. There's probably more than one way to do that. So I'll use a tree diagram. Don't write this. And we could have heads and tails. Probabilities would be 1/2 and 1/2. We could have heads and tails again. Probabilities are 1/2 and 1/2. We could have heads and tails again if the first one was tails. And then those are our first 2 flips. And the reason that I don't want you to draw a tree for this is because when we start getting into a tree diagram with 3 outcomes, it sure does get crowded and messy and hard to deal with. And that's why we're not going to fool with a tree diagram for this situation. Instead, what we are going to do, since, okay, we're going to flip a coin 3 times, I wonder what the sample space would look like. And if I just list out that sample space, maybe I can use that to answer this question. That's the goal of our tree diagram anyway, is to get to a place where we have the sample space and the probabilities that go with every outcome. So here, see, a coin's going to be flipped 3 times. Here's one that you might have to shake a little rust off, but how many outcomes will there be? How many different outcomes will I have if I flip a coin 3 times? And we're leaning back into something that we studied in the past. The fundamental principle of counting is what we want to think about as far as this one's concerned. Maybe that helps a little bit. All right, I'll go a little more straightforward then. On that first flip, how many possibilities are there? For the first flip of the coin, how many possibilities are there? How many things could possibly happen? Perfect, Jennifer. There are two. Right, Nadine. On the second coin flip, how many things could happen? Two. Yep. And then I'll do this one for you. On the third coin flip, there are two things that can happen. Fundamental principle of accounting says how many outcomes for each different stage in the problem, and then multiply those together. 2 times 2 times 2. We'll have 8 possible outcomes here when I flip a coin 3 times. Let's see if we can list those. Careful, Jennifer, we're multiplying. So we'll list these out. So I could get heads, heads, heads. I could get heads, heads, tails. And what I want you to think about when I'm writing down here is, let me back up just a minute. If I flip these 3 coins, they could all be heads. So that's the first thing we'll write down, all heads. And then I could have, well, what if they aren't all heads? What if there's one of them that's tails? Okay, well, I'm going to put the tails in the third spot. And what if the one of them that's tails is in the middle? And what if the one of them that's tails happens first? Okay, that's all the ways we could get one tails. Okay, well, now let's see, what if there's only one heads? And so I have heads in the last spot, heads in the middle spot, heads in the first spot, and then all tails. I know when this started, I was after 8 outcomes, and that's how many I've got. So I've got them all. So I've written down my sample space here. I have 8 outcomes. They're all equally likely. The probabilities of every one of these would be 1/2 times 1/2 times 1/2. And so now we want to know the probability of exactly 2 heads. Well, I can see just by looking at them that there are 8 different outcomes. So it's going to be 8 outcomes, and we just have to figure out how many successes there are. Exactly 2 heads. Exactly means no more, no less. There's 3 heads here, so that's no good. There's 2 heads there, that's good. 2 heads, 2 heads. Only 1 head, no good. Only one, and none. So it looks like I have 1, 2, 3 successes out of 8 outcomes. So the probability of getting exactly 2 heads would be 3 out of 8 or 3/8. Because this only has 8 outcomes, we just went ahead and listed the sample space because it's not a very big sample space. If we were flipping the coin 4 times and there were 16 outcomes, that'd be a little clumsier. We wouldn't want to do it this way. And that's kind of where we're going to head next, is with something that's a little more efficient than what we just did here. Okay. We're still flipping a coin 3 times, but instead of using the sample space, now what we're going to use is something called Pascal's triangle. It's named after a French, mathematician, Blaise Pascal, who came up with this. He was a mathematician in the 1600s. Very interesting person. He eventually came up with something called Pascal's wager that has to do with religion. It's a very interesting idea. I'll leave that to you. But here, we're going to use Pascal's triangle. This is going to be a very valuable tool for us. It looks like this over here, and we're going to talk about it here in just a second. You won't have to write the triangle down, even though it's not very hard to create one. But we're going to use Pascal's triangle when we're doing a problem that involves binomial probability, which means there are just 2 outcomes, like flipping a coin, heads and tails. There's only 2 outcomes. And we need those outcomes to be equally likely. It's, tails and heads are both 50% propositions. So they're equally likely outcomes. So that's why that's why we're allowed to use Pascal's triangle. Pascal's triangle is excellent. What Pascal's triangle does is helps us identify our outcomes and our successes. But first, let's take a look at this triangle and see how this gets built. So we start with a 1 up here in the very first row, which we're going to call row 0. And then below that, you'll see a 1 and a 1. And all the way along the outside edges, all the way down this thing, are just 1s. Every single time, all the way down the sides, it's just 1s. So let's look at how the rest of this thing gets built then. The way the rest of this gets built is, okay, I'm going to have a 1 on the outside edges. And then these two numbers come together. 1 plus 1, that's where I get the 2 from. In the next row, 1's on the outside edges. And then this 1 and this 2 make a 3. This 2 and this 1 make a 3. And so I could build as many rows as I needed to. I start with a 1. The next one's 1, 1. So the next one, I'm going to have 1's on the edges. I add these two numbers together to put a 2 in here. I know I'm going to have 1's on the outside edges. 1 and 2 makes 3. 2 and 1 makes 3. If I wanted to build the next row, I know I'm going to have 1's on the outside edges. 1 and 3 is going to make 4. 3 and 3 is going to make 6. 1 and 3 is going to make 4. And that's how we could build as many rows as we needed to of this triangle. With that in mind, now let's take a look at how we're going to use this triangle, what these numbers tell us. In this situation, we're looking at a problem that's exactly the same as what we did just a minute ago, where it said we're going to flip a coin 3 times. What's the probability of getting exactly 2 heads? So we're going to flip a coin 3 times. What's the probability of getting exactly 2 heads? Just as a reminder, you wouldn't need to do this when you're using Pascal's triangle, but just as a reminder, I'm going to jot down the outcomes that we came up with when we wrote down the sample space. We had all heads, we had 2 heads and a tail, we had 2 tails and a head, and all tails. We'll just keep that in mind. Those were the 8 outcomes that we came up with. If you see anything you're not sure of or you're confused about, you let me know. If you're thinking, still not seeing how this triangle works, that's totally fine. We haven't talked about it yet. All right, so here goes. We're going to flip this coin 3 times. And so because we're going to flip the coin 3 times, that lets us know that we are going to use row 3 of the triangle. And when I look at row 3 of the triangle, I see there's 1, 3, 3, 1 in there. Let's talk about that for a minute. There's 1, 3, 3, 1. That's the third row of the triangle. Because I'm flipping the coin 3 times, it's the only row in the whole triangle that I care about for this problem. What these numbers represent, this 1 right here, that is the number of ways that I could get 3 heads and no tails. So I'm going to go ahead and label that one as 3 heads and no tails. Moving over 1 spot, when I look at this 3 right here, that tells me the number of ways that I could get 2 heads and 1 tail. And if you're thinking, where are you getting these numbers from? Well, basically what I'm doing is, what the triangle does is it tells me how many of each of these there are. When I look over here and I say, okay, there's 3 heads, then I could also get 2 heads. And look at that, there's 3 ways that I could get 2 heads. So this is the number of ways that I could get 2 heads and 1 tail, because there are 3 of those. Okay, well, I'm seeing a pattern here. 3 heads, 2 heads. Is this the number of ways I could get 1 heads and 2 tails? Well, let's see. There's 2 tails, 1 heads and 2 tails. Sorry, 1 heads and 2 tails, 1 heads and 2 tails, 1 heads and 2 tails. Sure enough, there are 3 ways to do that. That's what the 3 tells me. And then finally, that 1 at the very end of this line, well, let's see. 3 heads, 2 heads, 1 heads. How about 0 heads? which means I would have 3 tails. According to Pascal's triangle, there's only one way to do that, and sure enough, only one of my outcomes in my sample space has 0 heads and 3 tails. What I've just done here with this row of the triangle, and a little clumsy the first time through it, but as you get used to this, it gets much, much quicker, is I use the row of the triangle that corresponded to the number of flips I'm going to make. And it tells me there's one way to have 3 heads and no tails, 3 ways to have 2 heads and 1 tail, 3 ways to have 1 head and 2 tails, 1 way to have no heads and 3 tails. That's all the possible outcomes. So one thing I can do is I can add these numbers together to get the total number of outcomes. 1 plus 3 plus 3 plus 1, that's going to be 8. So I'm going to have 8 outcomes. And then I just need to identify my successes. The probability of getting exactly 2 heads. Well, as I look at the labels that I put on here, I look for the ones that have exactly 2 heads. Well, that's these 3 outcomes right here. So I have 3 successes out of 8 outcomes. So the probability of getting exactly 2 heads is 3 out of 8. It's the same answer we got when we listed out the sample space and looked at it. This time, it was a little bit clumsy and mechanical because we were looking at this sample space over here. But as you get into this, you'll kind of see that, well, I don't really need to write this sample space down anymore. I just need to find the row of the triangle that I'm working with, give those labels, and then I'll be able to answer the question. One thing I do want to point out about this, and let me get rid of some stuff here, keeping in mind that 3/8 was our answer to this question. I don't want you to feel like, what if I label it incorrectly? Is that going to make things go sideways? Because it won't. It'll be just fine. You want to label it correctly. You want to be careful with that, but I don't want you to feel like there's a lot of like, what if I do the other way? Here's what I mean. We've got our 1, 3, 3, 1. When I labeled this a minute ago, I did, okay, this is 3 heads, which means no tails, 2 heads, which means 1 tails, 1 heads, which means 2 tails, and no heads, which means 3 tails. And you can see that I got 3 out of 8 for our probability here in this question. Well, what I want to make sure that you see is you could label it the other way and you're going to be just fine. What I mean is, if instead you said, what if I make this one 3 tails, which means no heads, 2 tails, which means 1 heads, 1 tails, which means 2 heads, and no tails, which means 3 heads. You want to make sure you go 3, 2, 1, 0, but it doesn't matter if this one over here is 3 tails or if this one over here is 3 heads. The reason for that, because you can see exactly 2 heads, that's going to be right here. It's still going to be 3 out of 8. The triangle is symmetric. So as long as you go 3, 2, 1, 0, it's fine. It doesn't matter if you call this one 3 heads or 3 tails. It's still going to work fine because the table is symmetric. It's going to be a mirror image either direction. Hopefully that makes sense. It's kind of a weird thing to figure out how to phrase. If I made it worse, or if you don't understand something, just let me know and we'll make sure we get it cleared up. All right, fantastic. Let's look at another one. We're going to flip a coin 3 times. We're going to use Pascal's triangle to answer this question. The reason we can use Pascal's triangle is this is binomial probability. We have 2 outcomes. They're equally likely, so we're good to use Pascal's triangle. This time the question says, you're going to flip a coin 3 times. What's the probability of getting at least 2 heads? Last time was exactly, this time is at least. That's going to change things a little bit for us. Those words definitely matter. We're flipping the coin 3 times. So we're going to look at row 3. So what we care about is 1, 3, 3, 1. Now we go into our labeling. And like I said, it doesn't matter which way you label it. So last time I did heads on the left. This time I'm going to say that's 3 tails, 2 tails, 1 tails, and no tails. Some of you have all the information you need to answer the question right there, but I don't know. I like to go ahead and finish off my label by putting the heads on there too. What I mean is, since there's 3 tails, that means there aren't going to be any heads. 2 tails means 1 heads. 1 tails means 2 heads. And no tails means there must be 3 heads. And now I've got my labels for everything. This question said, what's the probability of getting at least 2 heads? Probability is always successes over outcomes. So I want my 8 outcomes in the bottom. I just need to figure out how many successes are and put that in the numerator. All right, at least 2 heads. Well, this one has no heads, so that's no good. This one has 1 heads. That's not enough. This one has 2 heads, okay. This one has 3 heads. At least 2 means 2 or more, so we want to count those 2. So we'll add those together. Those 3 successes plus that 1 success means the probability of getting at least 2 heads is 4 out of 8. We didn't need to write down the sample space, which is awesome. That's kind of the beauty of Pascal's triangle, is it tells us how many ways there are to get no tails and 3 heads, 1 tails and 2 heads. So I don't need to write the sample space down. I can just use these numbers. Let me know if you have any questions on what we did there. A really important distinction between exactly and at least. If you have any questions, let me know. All right, fantastic. Now I want you to try one. A family wants to have 5 children. What is the probability that they get 3 boys and 2 girls? And I'm just going to let you try this. I'll set up a poll for it. My typing fingers are rusty. It's taking me forever. All right. So our approach here will be to identify the row that we care about. Once we have that row identified, then we need to label each of the different numbers that are in that row. Then we need to figure out our probability based on the most important thing about probability. Binomial probability is something that typically goes really well for students. So I hope the same thing is true for you. It's one of those things that as soon as the light bulb goes on with the triangle, then you just answer questions. It's not really not typically a challenging topic. But if you do have questions, you can let me know. Responses from the poll are not flooding in, so I may just We'll go another 15 seconds or so, or maybe I'll just kind of scrap it and we'll just talk about this one. Maybe we weren't quite ready for a poll yet. Yeah, I think we'll do that. I think we'll just get rid of that poll there. Let's go ahead and do this one together. I don't think we were ready for a poll. All right. So family wants to have 5 children. So since they're going to have 5 children, what we're going to need to do then is we're going to need to take a look at row 5. Sorry about that. We're going to look at row 5. And the numbers in row 5 are 1, 5, 10, 10, 5, and 1. Those are the numbers in row 5. If I want the total number of outcomes, I'm going to add those together. So that's something we're going to need to answer this probability question, is the number of outcomes. So we'll go ahead and add those together. 1 plus 5 plus 10, let's see, that's 16, and then there's 16 more. So there's going to be 32 total outcomes. Another way to get 32 outcomes there is they're going to have 5 children. 2 possibilities for the first one, 2 for the second, 2 for the third, 2 for the fourth, 2 for the fifth. Multiplying all those together, they're going to be 32 outcomes. So you could get the number of outcomes 2 different ways. You could multiply 2 by itself 5 times, or add the numbers that are in that row of Pascal's triangle. Okay, now we need a number of successes, and to get those, we're going to label each of these outcomes. We're talking about boys and girls, so they're going to have 5 children, so at most they could have 5 girls, or 4 girls, or 3 girls, 2 girls, 1 girl, no girls. To go along with that, this means there would be no boys, 1 boy, 2 boys, 3 boys, 4 boys, 5 boys. What we're saying here in each of these is there's one way to have 5 girls and no boys. Girl, 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 girl. That's it. There are 5 different ways to have 4 girls and a boy. You could have 4 girls and the boy could be first, he could be second, he could be third, he could be fourth, he could be fifth. 5 different ways to do that, and so on down the line here. We don't want to list out all 32 outcomes. Using the triangle is what allows us to avoid that. Now we just have to find our successes. 3 boys and 2 girls, so we just have to find that. 3 boys and 2 girls, that's right here. That's the only place in all of my outcomes listed where I have 3 boys and 2 girls. So there are 10 successes out of 32 outcomes. So the probability of getting 3 boys and 2 girls is 10 out of 32. Please let me know if you have questions on that, because I expected different response on the poll. Hopefully we've cleared it up, but maybe not. If there is something you want to ask about, now's a great time. I got you, Jennifer. That makes sense. Right. Remember, keep in mind that row corresponds to however many outcomes we're doing. When we're flipping 3 coins and we looked at row 3, we're having 5 kids, so we look at row 5. Because we need to make sure we're able to have all these labels on there that go from no girls all the way up to 5 girls, and from no boys all the way up to 5 boys. That's a good question, Shelby. Off the top of my head, I don't remember. I'm pretty sure that it's available for you. Obviously, for a quiz, you'd have it available because you can have your books and notes. On the exam, I will look that up and get back to you. I'm pretty sure that it's on the questions, but I don't want you to go into the exam with pretty sure. So I'll look it up and let you know. Definitely by Thursday. Okay, let's try another one. This time, family wants to have 4 children. So make sure you use row 4. And then my question for this poll will be, what's the probability they have at least one girl? Okay. Probability of at least one girl if the family has 4 children. So when we recognize binomial probability, 2 equally likely outcomes, that's when we can use Pascal's triangle. We make sure we identify the row based on how many trials there are going to be. If it's 3 coin flips, it's row 3. If it's 5 children, it's row 5. 4 children, row 4. Then we use the numbers in that row to come up with our outcomes and identify our successes. And that's how we get our probability. Where these numbers come from, in addition to being, you just add to go down a row, they also come from using the combination formula. But again, if you were in a probability course, we would talk about that, but it's okay if we don't talk about it in here. Let's go another 20 seconds on this, and then we'll talk about it. If you need more time, let me know. If you get an answer that's none of those, go ahead and pick the one that's closest to yours. All right, let's see how we did. Okay, we're unanimous. That's great news that it's unanimous. Not everybody was responded on this one either, so I do want to make sure you ask questions if you have them. I don't want you to not know how to do these, because using Pascal's triangle to find a probability is exactly what today's lesson and homework will be all about. All right, so as we dive into this one, they're going to have 4 children, so we're going to look at row 4. And in row 4, I see 1, 4, 6, 4, 1. Oh, perfect, Summer. That's awesome. That's very good news. Okay, so I can add those up to get the total number of outcomes, which would be 1 plus 4 is 5, and 6 is 11. So 4 is 15, 1 is 16. So I've got 16 outcomes. Another way to get 16 outcomes would be 2 times 2 times 2 times 2. Either way, we get to 16 outcomes. Now we want to label these. And let's see, they're having 4 children. So the highest number of boys they could have is 4. So this is the number way to have 4 boys, 3 boys, 2 boys, 1 boy, and no boys. And just to, oh, very good, Shelby. That's great news. Just to complete my labels here, then I'll have, if there's 4 boys, there's no girls, 1 girl, 2 girls, 3 girls, 4 girls. And this particular question said, what is the probability of getting at least one girl? So anywhere where I have one girl or more is, we want to count that as a success. Well, let's see, I have no girls here, so no good. One girl, yep. Two girls, well, that's at least one. Three girls, yeah, that's at least one. And four girls, yeah, that's at least one. So all of these are successes. So I'm going to add those together. 4 and 6 is 10, 14, one more makes 15. So the probability of getting at least one girl is 15 out of 16. The beauty here is we didn't have to make a tree diagram with 4 columns to show the 4 children. We didn't have to list the sample space with 16 different outcomes. We can use Pascal's triangle to help us answer this question. All right, let's try a couple more. A coin is to be flipped 6 times. So we know what row to use. What's the probability of getting exactly 4 heads? I'll set up a poll for this one. Since it's coin flips, that means there are 2 outcomes that are equally likely. That means we can use Pascal's triangle to answer the questions. Then we just have to kind of determine what the question's asking for. And from there, figure out, well, how many outcomes are there? How many successes there are? Kind of the reason for the mention about the most important thing about probability earlier today is anytime we're doing a probability question, we're looking at successes over outcomes. And if we can figure out how many outcomes there are, figure out how many successes there are, then we've figured out the probability. Let's go, I don't know, let's go another 20 seconds on this, and then we'll talk about it together. All right, let's see how we did on this one. All right, unanimous. That's great news. Okay, very good. That's how I expect these to go. So I think now we're in a place where we can feel really good about how we're doing. Main thing to keep in mind is the difference between exactly and at least. Here we're talking about a coin that's going to get flipped 6 times. So we know that means we're going to have to look here at row 6. If you're not sure what row it is, oh, sorry about that. Yeah, after a poll, my screen goes goofy. All right, if you're not sure what row it is, a really nice way to tell is just by looking at the second number over. What I mean by that is here in row 1, we know there's going to be 1s on the outside edges. The next number over, that tells us the row. It's row 1, it's row 2, it's row 3, it's row 4, it's row 5, it's row 6, it's row 7, it's row 8. So that number, the first one in from the left-hand side, will let you know what row you're in. Here we're looking for 6 flips So we're looking for row 6. That's going to be the one that has a 6 in that spot. And so it's 1, 6, 15, 20, 15, 6, 1. Now we'll need to go through and label these. And here we're talking about heads and tails. We're talking about coin flips. So I'm flipping it 6 times. So 6 heads, 5 heads, 4 heads, 3 heads, 2 heads, 1 heads, and 0 heads. If you're labeling and you find out you're going 6, 5, 4, 3, 2, 1, 0, -1, that can't be right. I must be in the wrong row. Or if the biggest number you get to is a 5 for heads, or you go 6, 5, 4, 3, 2, and you never get to 1 and 0, then you know you're in the wrong row. So that's a little self-check built in. This part you don't have to do, but I like to. 6 heads would mean no tails. Then 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, 6 tails. And just as a little reminder, what these numbers mean for us is there is one way to get 6 heads and no tails. There are 6 ways to get 5 heads and 1 tails. There are 15 different ways to get 4 heads and 2 tails. I don't want to write those down, which is exactly the beauty of using Pascal's triangle. Okay, so let's see the total number of outcomes. Well, I guess I can add those together. Let's see, that's 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, 64 outcomes. So I can put that in the denominator. And then I just need to find my successes. Probability of exactly 4 heads, no more, no less. So all I'm looking for is where there are 4 heads. That's right here. 15 successes out of 64 outcomes. So the probability of getting exactly 4 heads is 15 out of 64. Poll went great. Anybody have any questions about what I did there? I do want to point out one quick thing. I'm starting to feel like we're really comfortable, which is awesome, but I do want to point out that if you said, well, but I called this 6 tails, 5 tails, 4 tails, 3 tails, 2 tails, 1 tail, and 0 tails, which meant no heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, and 6 heads. If you labeled it that way instead, with 6 tails on the left instead of 6 heads, that's okay. You're going to get the exact same answer. We're looking for exactly 4 heads. That's right here. And now it's these 15 that would be your 15 successes. So you get the exact same answer, and it's because of the symmetry of Pascal's triangle. Any questions about this before I have you do one more? Okay. The coin is to be flipped 6 times. Find the probability of getting at least 2 tails. I'll set up a poll for this one and let you try it. We'll go another, I don't know, let's say 20 seconds on this. If you need more time, let me know. If you get an answer different from the one shown, just pick the one closest to yours and then we'll talk about them. All right, let's take a look at this one. Not unanimous, but strong agreement. Okay, it's not a bad place for us to be. Let's go ahead and take a look at this and make sure that we're all in the same place. Let me know if you have any questions about it. Okay, so when we look at this one, we can see that a coin is going to be flipped 6 times. And since it's going to be flipped 6 times, we want to make sure we're using row 6. Same as last time, which is 1, 6, 15, 20, 15, 6, and 1. Oh, perfect, Summer. That's awesome. So we were unanimous there. It just didn't look like it. That's great to hear. All right, I'll go through this relatively quickly then. Adding those all up or doing 2 raised to the 6th power, because we could do it that way also. We can see that there are 64 outcomes. Now we just need to figure out how many successes we're going to have. And when you label these, I'll do 6 heads, 5 heads, 4 heads, 3 heads, 2 heads, 1 heads, 0 heads, which means 0 tails, 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, 6 tails. Then we just have to make sure we identify our successes properly. At least 2 tails. There's no tails here. There's 1 tail here, 2 tails. All right, 3 tails. At least 2 means 2 or more. So yeah, that's good. 4 tails, sure. 5 tails, those are successes. 6 tails, those are successes. We'll have to add all these successes together. And let's see, when we do that, we have 15 plus 20 plus 15 plus 6 plus 1. That's 57 out of 64. And so the probability of getting at least 2 tails is 57 out of 64. In case we're asked to write a probability as a decimal, because that can happen sometimes, let's say a decimal rounded to the nearest hundredth, we just divide this. 57 divided by 64. When we do that, we get 0.8906. And that keeps going. If we want to round this to the nearest hundredth, and we just need to identify the hundreds place, look 1 space to the right, that's 4 or lower. So we'd round this down to 0.89. Since we did a reminder about theoretical and experimental probability, seemed like a good time to do a reminder about writing probabilities as decimals.